Okay, so when you talk about the intermolecular force and the force holding solid and liquids together. Now, in chapter 5, at the beginning of chapter 5, I gave you a diagram there. The solid matter, all the particles are compactly held together, and they're being packed in a very orderly fashion. Liquid, there's a little bit disorder. Gas molecules are all over the place. Okay, so the intermolecular forces are the forces holding solids and liquids molecules together. Now, the term inter means the forces are in between two molecules. It's not like the chemical bound. The chemical bound is actually within the molecule, inside the molecule. Okay, so the intermolecular forces refers to the forces, attraction forces between the molecules. There, intermolecular forces are also collectively called van der Waals forces. And now you know this name at the end of chapter 5 there when we're discussing the corrections for the ideal gas law. The Dutch scientist van der Waals, and he studied a lot of these different types of properties of the solid and liquid there. So when we name these forces van der Waals forces in honor of his research and study, and help us to understand how molecules interact with one another. And here, one thing that we must make sure that people understand, intermolecular forces are not chemical bound. Chemical bonds are something within the molecule, intermolecular, means between the molecules there. And there's that's a key difference there. Now, the intermolecular forces exist simply because you do have charges. You have equal number of charges of positive charge and negative charge in the neutral molecule, but you do have charges in there. Okay? And you do have ions there. So because of those charges there, they are going to be attracted to one another, repelling to one another. Polarity. When you have molecular compounds there, and we can clarify the chemical bound into classify chemical bound into polar bound and non-polar bound. So polarity, and in terms of the net dipole, if you will, separation of the charges within the molecule between the two atoms connected by a chemical bound, and also the geometry, well, that actually has an effect on the intermolecular forces, and also simply the size of the molecule, the size of the atom, has something to do with intermolecular forces. So these are the things that we want to take a look at. Now, when you look at the intermolecular forces there, in terms of the gas, intermolecular forces are weak enough so that we can, under normal conditions, room temperature, low pressure, and we can completely ignore the intermolecular forces. Using ideal gas law, PV equals nRT, we can make fairly accurate calculations. But when you start talking about the liquid and solid, and intermolecular forces becomes a little bit stronger. And sometimes then you have to take that into consideration when you try to understand the properties of liquid and solid there. And the solid has very strong intermolecular forces there, especially for molecular compounds and molecular solids there, even for metals there. And we don't use the term molecule to describe ionic compounds there, but in solid, there's a very strong intermolecular force. So that's the relative strength of the intermolecular forces there. So for liquid and solid, intermolecular force is an important factor that you have to consider when you try to understand the behavior of the different types of solids and liquids there. Okay. Now, the importance of the intermolecular forces is that it influences the chemistry in many ways of different molecules. Like they're directly related to the properties such as melting point, boiling point, okay, and also energy needed to convert substance from solid to liquid, liquid to gas. I'm using water as an example there. Okay. Now, water molecules will interact with one another. When you draw a Lewis structure of water molecule, and you know this is what it is looked like, and you get four electron groups around the central atom oxygen. Two of them are bounding pairs, and two of them are lone pairs. We were in lab, we were talking about that. Okay, so in this case, and there are four groups of electrons surrounding the central atom there. Now water molecule will be able to interact with one another, resulting in a fairly strong attraction between one another. Okay, and it has something to do, because of that attraction, and it has something to do with the boiling point and melting point of the amount of energy that is required to convert liquid water into gas water vapor, is fairly high, and you actually have to heat it up pretty strongly to convert it into vapor there. And then we want to take a look at the interaction, the intermolecular forces between the water molecules there, so we can understand why they have such a high, why water molecules, water has such a high boiling point, and then why does it take so much energy to convert liquid water into gaseous water there. And also, they're important in determining what we call the solubility. We know that alcohol can dissolve and can mix with water, and can dissolve in water. The oil cannot. Why is that? It's simply because alcohol molecules have similar intermolecular forces with water molecules, and therefore they can mix with one another, where the oil molecules in the oil, have completely different intermolecular forces. Therefore, when you put oil in water, they are not going to mix, and they're going to separate. And because of the density there, oil most of the time will be floating on top of water there. And also they're critical in determining the structure of biologically important molecules such as DNA and protein. So we need to understand the property of the intermolecular forces there, so that we can understand these things better. Okay, so talking about intermolecular forces there, how strong is intermolecular force? Well, it's weak. It's not strong. If you have hydrogen chloride molecule, the chemical bond between a hydrogen atom and chlorine stores a lot of energy, 432 kilojoules per mole of energy. Meaning, if you try to break HCl bound, you have to supply 432 kilojoules per mole of energy. Now, if you have a polar molecule like HCl, and if you have another polar molecule like HCl, we know chlorine group 7A, high electronegativity. So this end of the molecule is going to be slightly negatively charged, and this end will be positively charged. So if you have another molecule here, the same kind or different, well, the negatively charged part in one molecule will be attracted to the positively charged part of the molecule, of the other molecule there. Now, that's the attraction there. That's what we call the intermolecular forces. Magnitude, about 20 to 30 kilojoules per mole. Compared to the chemical bound, that's 20 times lower than the strength of the chemical bound there. So intermolecular forces are much weaker than the bounds that make up the chemical there. Okay, so they're not chemical bound. They're in between the molecule. Chemical bound is something within the molecule. Okay. Intermolecular forces in terms of the magnitude, in terms of the strength, and the IMF, that's intermolecular forces there. Okay. For comparison to the chemical bound there, it's about 1/20th of the strength comparing to the chemical bound there. And that's the key thing to remember. It does exist, but it's not a very strong force there. Now, when you deal with intermolecular forces there, when you try to study intermolecular force, you have to separate the compound that we're talking about. You have to separate them into different categories there, because different types of molecules, and they will have different types of intermolecular forces there. So we want to take a look at polar molecule versus non-polar molecule. What kind of intermolecular forces that we have here? Now, for the intermolecular forces in the polar